This video covers statistical part-of-speech tagging. I'll provide some intuition behind statistical part-of-speech tagging, and then move into a discussion of a Bigram HMM part-of-speech tagger. I'll walk through the equations necessary for building this kind of model, and then work through a case example. Statistical part-of-speech taggers predict part-of-speech tags based on their probabilities of occurrence, and these probabilities are learned from training corpora. For example, you might take all of Wikipedia, have someone manually assign part-of-speech labels to every single token, and then learn to predict part-of-speech tags for new text samples based on the tag distributions in the training corpus. A really simple statistical part-of-speech tagger could just work like what you see here. Using a training corpus, you could determine the most frequent tag for each word in a new test sample. You could then assign part-of-speech tags to the words in the new test sample based on those frequencies. For example, if I is used as a personal pronoun 95% of the time in the training corpus, you'd always predict that the word was a personal pronoun when you saw it. On top of that, if you encounter new words in the test sample that didn't exist in the training corpus, you could just assume that they were nouns based on the notion that the majority of previously unseen words are nouns. So you'd end up with labels like what you see here. And this actually isn't a bad heuristic at all. It reaches approximately 90% accuracy in general. However, we can still do a lot better than that by creating slightly more complex statistical models. One method that has been popular for this purpose in the past is using HMMs to predict part-of-speech labels. We learned about HMMs early on in this course, and an HMM part-of-speech tagger works by selecting the most likely tag sequence for a sequence of observed words. In doing so, it attempts to maximize the formula here. More formally, if you have states T corresponding to possible tags, and observations W corresponding to vocabulary words, you want to find the most probable sequence of tags T to underlie the observed sequence of words W. For the example going forward in this video, we'll assume that previous in tags just means the previous one word in tag, thereby creating a Bigram HMM tagger, but it could be trivially extended to whatever value of n you felt was appropriate for your needs. So we have a Bigram HMM tagger. This means that to determine the tag T sub I for a single word W sub I, we need to find the tag that maximizes the equation here, where we're multiplying the probability of a tag at the current index, given the tag that was at the previous index, times the probability of the word at the current index given the tag that is being considered. We can compute both of these probabilities from existing text corpora. Fortunately, the Penn tree bank and the Brown corpus both already contain a huge number of text samples with full manual part-of-speech annotations. Once we are able to find these probabilities, we can then proceed to find the optimal sequence of tags using the Viterbi algorithm. We can work through an example to see how this works. This example is from a previous version of the course textbook, but the current version of the course textbook has another nice example that you can read through also. So in this example, we have a sentence, Secretariat is expected to race tomorrow, and we have two possible tag sequences because maybe Secretariat is racing against another horse or turtle or whatever, or maybe Secretariat is going to a race. Intuitively, as humans, we can tell that it's probably the first case, but it's not necessarily so obvious for a machine. We'll use the Brown corpus tag set in this example. For the purpose of the example, it's pretty similar to the Penn tree bank. However, it contains a special tag for the infinitive use of to, as we can see here, and it also contains a tag for adverbial nouns. So it labels tomorrow as an adverbial noun rather than a singular common noun. Since we're creating a Bigram HMM tagger, we don't actually need the full context leading up to our ambiguous word. We just need to focus on the subsequence to race tomorrow. We'll take this subsequence and we'll create a little Markov chain for it. So we have a start state and then we have 4 different part-of-speech tag states. We also have all the different possible transitions between those states. However, we don't quite need all of those transitions for the subsequence we're looking at. We really just need 4 of them circled here. We need the transition probability from to to verb, the transition probability from to noun, the transition probability from verb to adverbial noun, and the transition probability from noun to adverbial noun. We'll compute those transition probabilities using the Brown corpus, where we can easily get frequency counts for each possible transition. So to find the probability of a tag at the current time given the previous tag, we would just get the number of times that tag followed the previous tag, divided by the total number of times the previous tag occurred in the corpus. So we start out by computing the probability of a noun given the infinitive to. We check the Brown corpus, and based on the tag frequencies, this is going to result in a probability of 0.00047. And next, we'll find the probability of a verb given the infinitive to. And based on the Brown corpus frequency counts, we find that this probability is much higher, 0.83. Next, we'll find the probability of an adverbial noun given a verb, and based on the Brown corpus frequencies, we see that that's pretty low, 0.0027. And finally, we'll get the probability of an adverbial noun given a noun. This is actually even lower than the previous probability, 0.0012. So we have our transition probabilities now, but we're not finished yet. Next, we need to compute the observation likelihoods for seeing race given that the tag is a verb and race given that the tag is a noun. We do that using Brown corpus frequency counts as well. So we find that the observation likelihood for the word race being observed given that the tag is verb is 0.00012. The probability of race being observed given that the tag is a noun is a bit higher, 0.00057. Now we can finally put everything together. We need to find the tag that maximizes the probability you see here. So we're multiplying the probability of the tag being either verb or noun, given that the previous tag was to, times the probability of the tag being adverbial noun, given that the previous tag was either verb or noun, times the probability of the word race, given that the previous tag was either verb or noun. We do this and we find that the probability for the first tag sequence is 0.0000027, and the probability for the second tag sequence is 0.00000000032. So the first tag sequence has a higher probability, and that's the one that our model will select. If we'd visualize the previous process in a Viterbi trellis, it would look like what you see here. So in the previous example, we predicted a part-of-speech tag sequence using our Bigram HMM Tagger. What if instead of a bigram model, we'd used a trigram model or even something with a higher end value? In general, more context leads to more accurate predictions, so the resulting model would probably perform even better. However, greater values of n also result in a lot more computational overhead, so it's important to consider the trade-off between resource efficiency and accuracy when designing your models.